Hello everyone. In this video, I'm going to cover lesson 13-2 on minimum spanning trees. The learning objectives for this lesson include defining what is the minimum spanning tree problem and defining a minimum spanning tree. Then we're going to implement and analyze an algorithm for creating minimum spanning trees. Specifically, we're going to look at Prim's algorithm. So let's take a look at the minimum spanning tree problem. Suppose we have a connected undirected graph G, and we want to construct a second graph from G called G2 such that it has all of the same vertices in G2 as in G. Note that the set V is the same. But G2 is going to have a subset of the edges in G. So we'll call G2's edge set E2 and G's edge set E. So E2 is going to be a subset of E. Now, if we select edges from E to form E2 such that the sum of all of the edge weights in E2 is minimized, yet every node in V is connected by some path over the set of edges in G2, E2, with no cycles, then G2 is actually a tree that spans every node in V with minimum total edge weight. Such minimum weight spanning trees are useful for a variety of applications. For example, sending messages from peer-to-peers in a network, and laying cables to connect homes. For these cases, a minimum spanning tree would represent the least expensive path in terms of time to connect each peer for our first example, or in terms of money for laying cable to connect cable to each home in our second example. The formal definition for a minimum spanning tree, or an MST, of a graph G comprised of the set of vertices V and the set of edges E is an acyclic subset of E that connects all vertices in V such that the sum of the weights in the MST is minimized. Now, there are several algorithms for constructing a MST, including these three here. We're going to cover Prim's algorithm in today's lesson. Now, all three of these algorithms I listed here, including Prim's algorithm, are greedy algorithms, meaning that they're always going to choose the locally optimal choice at each iteration. This may not generate the most optimal global solution. For example, if there is a more optimal global solution with less optimal local choices, greedy algorithms typically will not find it. So let's dive right into Prim's algorithm. For Prim's algorithm, the locally optimal best choice is defined as following an edge with the lowest edge weight. We will only add an edge to the MST that connects to a vertex that is not yet in the spanning tree. This is going to prevent cycles from being formed, which is what we want since an MST is a tree, an acyclic graph. Prim's algorithm has many similarities to Dijkstra's algorithm. In fact, the entire first part of the algorithm is going to look just like Dijkstra's algorithm. They are both going to initialize vertices in the same way and make use of a priority queue that visits each node once. So here's the algorithm in pseudocode. We're going to use the same vertex class as we did in our Dijkstra lesson. In that case, we have two additional class attributes, distance and predecessor. We're going to initialize all vertices distances to infinity and all vertices predecessors to 0. Next, we're going to enqueue all vertices into the priority queue unvisited queue. This will be the same priority queue implementation that we used previously for Dijkstra's algorithm. We're going to set the origin vertex distance to 0. And while there are vertices in the unvisited queue to process, we're going to dequeue the vertex that has the highest priority. And here's where the deviation begins from Dijkstra's algorithm. We're going to compute a new cost, which really doesn't require any computation at all. This is simply going to be the edge weight between cur V and adjacent V. In Dijkstra's algorithm, we were actually summing up the hypothetical path from adjacent V through cur V back to the starting vertex. in Prim's algorithm, if the adjacent v is in the unvisited queue and the new cost is smaller than adjacent v's current path distance, then we're going to update adjacent v's current path distance to new cost. We have found a shorter edge coming into adjacent v. We'll set adjacent v's predecessor to cur v, and we're going to update unvisited queue with adjacent v's new priority, which is new cost, which is essentially representing the shortest edge weight we've discovered so far coming in to adjacent v. I have an example here that we can walk through. In this example, we have vertices A, B, C, D, E, F, G, and our starting vertex is vertex D. So all of these vertices initially start in our unvisited queue, priority queue, and we are going to dequeue from the unvisited queue the vertex that has the highest priority. And essentially the highest priority is D because its priority is set to 0, whereas all the other vertices priority is set to infinity. So we dequeue D, and then we look at all of the vertices that are adjacent to D, and we're going to select the edge that has the smallest edge weight. So the edge between D and A is 5, which is smaller than 9, 15, and 6. So we're going to update A's predecessor to be D and set the new cost to 5. Moving on, in our priority queue, the next lowest edge weight is going to be 6, connecting D and F. Our next lowest edge weight is going to be 7, connecting A and B. Our next lowest edge weight, highest priority, is going to be 7, connecting B and E. Next, our lowest edge weight of highest priority is going to connect C and E of 5. And then lastly, we only need to add one more edge, which we need to connect G, and the shortest edge is going to be through 9. Note that we cannot add this edge here because that would create a cycle. Now let's take a look at the implementation for Prim's algorithm. We're going to use the same binary heap class, vertex class, and graph class as for Dijkstra's implementation. So we're able to scroll through this code because we have already covered it and seen it in action. Okay, here is Prim's algorithm implemented. So we see our priority queue is based on our binary heap. We set the starting vertex distance to 0, and then we're going to build a heap out of all of the vertices and their current edge weights, or their current distances, distant attributes, which are set to infinity, which is the max size for an integer in Python. And while our priority queue is not empty, then we're going to process the vertex with the highest priority and walk through all of the adjacent vertices to our current vertex and try to find a smaller weight. If we find a smaller weight, then we're going to update our adjacent v for this small weight. Its distance is going to be the new weight, and its predecessor associated with this weight is cur v. And we're going to update adjacent v in our priority queue by calling our decrease key method with this new edge weight, new cost. Now, this next function, display prim results, I have utilized NetworkX to visualize the tree associated with Prim's algorithm, the minimum spanning tree. So it'll be a nice way to visualize the results instead of printing out the predecessors. The graph I'm going to use for this example is Miller-Raynham's Prim's example graph. So let me go ahead and show you what that looks like. here. So the vertices are A, B, C, D, E, F, G, and as you can see, there are a lot of 1s in this graph. In fact, the minimum spanning tree is going to choose all of these 1 edges with weight 1, and then the only vertex that does not have an edge 1 weight associated with it is A. It has a 2 and a 3. So the minimum edge weight to connect A to the rest of the graph is through B with edge weight 2. So let's go ahead and run this algorithm. And here's our NetworkX visualized minimum spanning tree. And we do see that C, B, D, E, F, and G are all connected with edge weight 1, and there's that connection between A and B with 2. The performance of prim is the same big O as our Dijkstra's algorithm. It's big O of V plus E, number of vertices plus number of edges, times the log of V, which is the number of vertices in the graph. Here are some example problems to work through related to prim's algorithm.